heat transfer example problem. Processor in uniform parallel flow with constant surface heat flux. A computer processor generates heat that has to be removed to keep the processor temperature from reaching its design maximum of 70 degrees Celsius. A cooling fan is installed to blow air over the processor. The air is at a temperature of 20 degrees Celsius and has a velocity of 5 meters per second. For a maximum power of 226 milliwatts, for part A, find the maximum processor temperature, and for part B, find the average surface temperature. To solve this problem, model the processor as a flat plate with length and width of 0.854 centimeters. Our first assumption for this problem is steady, uniform free stream velocity and temperature flow over the processor that is aligned with the flow with negligible end effects. More specifically, the flow is being modeled as a two-dimensional boundary layer. This is a significant assumption for the airflow from a fan over a processor and is an example of using an ideal flow to approximate a real-world case. Thus, we should be aware that our results have an uncertainty of about plus or minus 20%. Our second assumption is constant properties for each of our two cases, which is reasonable as long as the properties have less than a 10% variation over the range of conditions. Our third assumption is that there is negligible radiation for the exterior boundary. This is a reasonable assumption for moderate temperatures combined with significant convection at the exterior boundary. Our fourth assumption is that all the power generated in the chip results in a uniform surface heat flux on the top of the chip. This is certainly not true, but it will give us a high estimate for the surface temperature. Thus, it will be a conservative estimate in terms of ensuring the chip does not exceed the maximum temperature. Our fifth assumption is that the boundary layer transition from laminar to turbulent occurs at a critical Reynolds number of 5 times 10 to the fifth. Our sixth assumption is that air is an ideal gas which will be used to look up properties. For part A, to calculate the maximum surface temperature, we begin by writing Newton's law of cooling for the local surface heat flux in terms of the local convection coefficient, which is needed to solve for the local surface temperature. Also, we note that we will later need a local Nusselt number correlation to find the convection coefficient. Next, we solve for surface temperature in terms of the total power generated by the chip divided by the surface area for convection from the top of the chip. Finally, we note that since the boundary layer is thinnest at the leading edge and grows in thickness along the chip, the convection coefficient will be highest at x equals 0 and decrease with x. Thus, the maximum temperature will be at the end of the chip, where x equals L. To begin the process of selecting a Nusselt number correlation, we note that for boundary layers, properties are usually evaluated at the film temperature. For this case, since we do not know this value yet, we will need to iterate for a solution. To begin, we guess a value of 300 Kelvin, which is reasonable because it is higher than the bulk fluid temperature and the chip is dissipating heat. Next, we check the flow regime by evaluating the Reynolds number. We find that the value is very low and the flow is definitely laminar. For this laminar flow, we can use a correlation that is derived from the Blasius solution and the modified Reynolds analogy. Plugging in values, we get a Nusselt number of 21. From the definition of the Nusselt number, we get a convection coefficient of 64 watts per meter squared Kelvin. Finally, we get a maximum surface temperature at the end of the plate of 68 degrees Celsius. Before continuing, we will do one iteration cycle to ensure that the solution has converged sufficiently. We see that the film temperature is about 17 degrees higher than we guessed. Thus, we look up the properties at this temperature and repeat all of the calculations to get a new answer that is less than 1% different than our original calculation. Thus, given the uncertainty of these calculations, this answer has definitely converged with sufficient accuracy. Before moving on to part B, we will look at a plot of surface temperature versus location along the chip using the same equation used to calculate the temperature at the end of the chip. We see that, as expected, the surface temperature is the same as the free stream temperature at the leading edge at x equals 0, and then increases as we go further downstream due to boundary layer growth. Finally, the maximum temperature is indeed at the end of the chip at 0.854 centimeters. In addition to these results for laminar flow, let us consider how surface temperature would change for turbulent flow. Because the Reynolds number is so low for this example, we will instead use the conditions from example 11 with a much higher velocity of 40 meters per second and plate length of 1 meter. Thus, the Reynolds number at the end of the plate is much higher and in fact just above transition. The resulting surface temperatures versus distance along the plate are plotted here for 3 cases: all laminar, trip to turbulent at the leading edge, and for a mixed boundary layer that trips from laminar to turbulent. Note that all 3 begin at the leading edge at the free stream temperature of 30 degrees Celsius and then increase along the plate. The turbulent boundary layer stays much cooler due to the turbulent mixing and enhanced heat transfer. The mixed boundary layer initially follows the laminar curve, and then when it trips to turbulent, it has the same shape as the turbulent curve, but must start along this trajectory from a higher temperature. For part B, to calculate the area average surface temperature, we integrate the surface temperature over the surface and divide by the area. Substituting in the equation from part A and our Nusselt number correlation, we begin our integration by noting that for a two-dimensional flow, we only need to integrate in the x direction. Making sure to include the definition of Reynolds number that includes x, redefining Reynolds number in terms of L, and integrating, we get the result shown. Plugging in values, we get an average surface temperature of 53 degrees Celsius. Note that we could use this result to reevaluate properties and repeat this calculation, but based on part A, this will not result in a change greater than 1%. Thus, we conclude it is not necessary based on the limited accuracy of these results.